Hi guys, welcome to Learning Electronics Repair. And that was a little bit slow there.
Yeah, I was. Hey guys.
Never mind, we still get some hi guys. You've got both highs there. So back again with the PCBWay sponsored video. And this is the one where we're looking at making front panels for your projects using a PCB.
Yep.
FR4. And this has been evolving slightly, so let me just explain where we were up to. This is the schematic for the RF signal generator, which we're going to build into this front panel PCB. Detlef was looking at this in particular last time we were here, and he explained how this power supply works. So this is your Arduino Nano, and we have a 9-volt battery. Remind everybody how that actually worked.
Oh, me.
You.
The Nano itself has a little linear regulator, an LDO on the board itself. So you can put up to, I think, 12 volts.
Okay.
12 volt would really push it, but and this regulates it down to 5. So on the PCB, it's a bit different than we see already here in the schematics. And schematics use a 9-volt battery, simply pushes into the VIN. That would be the input of the regulator, and then they use a 5-volt output of that.
Here.
That's where Richard now is pointing. To power the modules, so the function generator, and the OLED is powered by the 5-volt.
So this is a net, we would call it.
Yeah,
this little thing. Okay.
Yeah, indeed it is.
Okay,
Yeah.
so
we were talking about this, and we were going for, okay, it works, let's keep it going, because right now we are simply putting in 5-volt in the VIN.
Yeah, here.
And the LDO is still in the path there. So this drops about 0.9 volts.
Yes,
something. We're going down to 4.1 volt on the 5-volt. And we were going for, okay, it works, so never touch a running system, guys. When I was thinking about this later, I thought, okay, we're running the LDO out of specs here. This could be a problem in the long run. So I said to Richard, okay, come on, if we want to do this right, we simply put the 5-volt in the 5-volt, and then we're fine. And we're actually trying this right now.
Exactly. So I didn't take much persuading. We've gone along with this. So if we just go over to the bench.
Oh, bench. There we go.
And we have our project. So originally we had the 5 volts coming in where it shows an 8-volt regulator, and the out of this was going, you can see, into the little Arduino on the pin that Det mentioned, which is VIN. Okay, so the regulator is on here. I'm guessing it's under the PCB. I don't see it, but
yeah, it's under the PCB.
Yeah, it's under there. So what I've done now is I've connected the ground to the same point. This is ground, but the 5 volts is now coming in over here. You'll see this track goes here, the 4th pin up on the Arduino, and I'll find something to point with better than my finger. It's now going to the 5 volt. So we're just bypassing that. That actually means that the inductor isn't used, this capacitor isn't used. I think all these were filters on that. But as a byproduct, it also means the power LED doesn't work, because the power LED here was connected to that. You can see there, yeah? That's the ground end, and the other end via a resistor, I'm sure somewhere, over here, was connected to there. So basically, the power LED isn't working, but we can get around that. That's not a problem. So let's see if this works. I'm now going to feed 5 volts directly into here from my bench power supply.
Okay.
And there we are. So my power supply is slightly leaning over. Really. We have the leads from the power supply, so I'm just going to connect them onto here. This is the ground, or 0 volts. The orange wire is the power in, 5 volts. And this should now work.
So,
oops, get a connection on it. And it does. We see a green light's gone here, the thing's working.
There we go.
And if you look at the power supply, 60 milliamps, which is what it was drawing previously. So
we don't even get more or less power drain there.
Yeah. In fact, we can even prove this is working properly, because if we go to the pins on the display, when I was here before, we had 4.1 volts.
In the episode before this.
Which, by the way, I will link from the video description. So we have the wrong way round. We have
strange. I never care about this, because I know that I only want to measure.
Well, I'd agree with that, but you'd be surprised surprised how many subscribers want to know why it's running on a negative supply.
All right. Okay.
5.035. So that's running now at 5 volts, not 4.1.
Yeah, this is maybe me being a bit pedantic, but I think it's better that way.
I actually agree that it's better.
Thank you.
It's better that way.
Okay. So next part we were going to do makes this battery powered, and last time we were talking about this, and we did this on a live stream actually. We had a module here that we tried out, and in fact it didn't work. It just the only thing it did, it converted electrical energy into heat. And Richard and Carlos tried to salvage the thing, and I said, this costs cents, don't do this please.
Yeah. There was actually a short circuit on the output from the module. So the module is this thing.
Yeah, let's get this in shot.
Let's get to the shot. And Det's patented don't short anything out protection system. So
since it's not mounted to anything, this was the only way to, because this is connected to a LiPo right now, and we didn't want to have this floating around, flapping in the breeze like some famous YouTuber says. Okay, so we have our module, and then if we just rearrange this a little bit more, so we can show to the people
the whole thing, and here it is.
Yeah.
Okay, more plastic bags than you can shake a stick. Have you tried condoms?
That's an idea. That's very creative. Yeah. So what you see here is a USB-C connector for the voltage in. So this will be used for charging and powering the whole thing. This little module is a complete power bank. So everything is in there that you need to run this. So it takes 5 volt, charges the battery. While it's charging, it puts the 5 volt out to the 5 volt out. So you can run a thing while it's charging. It's not bad. And for currently I'm using this LiPo cell over here. This is a protected one to power the whole shebang. So as you see, currently this isn't connected.
Okay, so if you look at the output voltage, this is where we're going to connect our load, which is this. The reason for the USB is so you can actually use this as a 5 volt power bank, a charger for your phone or something like that. Okay.
Yeah. For emergency uses there.
Yeah, just another handy use of it. What's this yellow wire for? Oh, I know what it's for.
This is voltage in, so we can measure the current that is floating. Maybe we're going to do this first.
Okay.
You know?
Yeah. So at the moment we have the battery disconnected.
Yeah.
But because this is connected, this, what we call a management unit.
Yeah, power bank unit.
Okay.
Charger.
There will be some drain on the battery, even when this, if we put an on-off switch in here, is switched off.
Yeah.
Okay.
The data sheet says something that the standby current should be 100 microamps or something. So I could live with 100 microamps, but let's measure this.
Okay.
So you want to do the honors?
I will with my multimeter that I've just connected up wrong, and let's see if it still works.
Let's see if it's still alive.
So we go to milliamps range.
All right. And you simply connect between these two.
The red and the yellow. So this is the power draw when we have no load.
Yeah.
Okay. And we have about...
Low, this is low.
Let's go to microamps. That's milliamps. It's very low. Let's go to microamps. So we have about 50...
This is even better than the datasheet.
50 microamps.
Datasheet mentions 100 microamps. Yeah. So
I take this changing slightly because this whole control unit is changing slightly.
Yeah, it probably is pulsing there because it keeps a voltage on the output right now, and if it detects a voltage drop there, it simply switches into 5 volt mode.
Yeah.
But 50 mics, we can live with that, right?
We can definitely live with that. Yeah. So
we have a LiPo here. This will be probably the LiPo we're going to use. On the package it says 3,200. Let's be optimistic and say it's 3,000.
Okay, and we're interested to see how long this can work in standby. The reason of this, guys, as Det pointed out, is that if we put an on-off switch in here, then you can't charge the battery without the thing switched on.
Yeah, this would be bad.
So you really want this permanently connected to here. So we're going to have like 50 microamps coming like this all the time, even when we're not using it. Yeah. So I said to Det, well, how long do you think we can run this for?
The battery life calculator.
Before the battery goes flat. Hours, days, and Det says, days, weeks maybe.
Yeah.
So then Detlef had a bright idea. He says, well, online there's a battery life calculator. So let's have a look and see how long this will run. from a 3,000 milliamp hour battery.
Yep.
You guys, if you want, get into the comments below, put a timestamp and say how long you think it's going to be.
If you're playing along at home. Yep.
Yeah, but if you are playing along, don't just do what we're going to do now, because otherwise there's no point in playing. Yeah. Okay, so we'll go for battery life calculator.
Yep, indeed.
Okay.
What do you type there?
I put something close enough.
Yeah, close enough indeed.
Battery life calculator.
And look, it's coming from DigiKeys.
Yep,
oh, nice.
DigiKey will do just fine. So
all right.
We go here.
I trust DigiKeys here.
I will go along with this. We are in Spain, but we'll probably go to Spanish if I do that.
Switch to Spanish if we do that.
So battery capacity was, what was it, 3,000?
Yeah, let's be
not 399.
optimistic here and let's say we get 3,000.
Well, if we were optimistic, we'd say 3,200. That's its rating value.
No, come on. I guess from the weight here, this would be 2,000 something.
Not that optimistic.
No.
And the consumption, well, we can go into...
Do we have microamps?
No.
Oh, we don't have microamps, okay.
But we can do it. So 1 here would be 100 microamps. So 0.5 is 50. Mm-hmm. 6,000 hours, it says. Yeah, 6,000.
Sounds like this is enough.
It sounds like enough. So
can you switch it to something? Oh, yeah. Perfect. Go for years.
Years. So 6.8 years this will run before the battery goes flat. Now, I think, although I don't use this thing all the time, I'll probably use it a bit more often than that. Also, bear in mind, if the battery does go flat, well, you just stick a charger into it. It wasn't meant to be a portable device, but it could be a portable device.
This way it is, yeah.
Yeah, I mean, normally I'm using this on the bench, but yeah, it could be portable. Yeah. And I wouldn't worry about it much until about 2030.
Right, you're right, yeah. 6 years, yeah.
Yeah, plus or minus.
Yeah, so you can leave it on the shelf till 2027.
I suppose we could put two of these things in parallel.
I'm still not happy with that, because you could do that, but you need to balance the cells here. And,
okay.
If they are not discharged like they are right now, this is not a good idea.
In that case, let's
go
with 6. Let's go with 6.8 years.
6.8 years would be fine.
Okay, so
so even if the cells only 2,000 milliamps, we're still talking about 4 years of battery life. Okay. So standby, we're fine. By the way, there's an alternative to this. You could use not a all-in-one module like we're doing right now. You could use one of these modules where they have a TP4056 or a battery charging thing with a projection cell on this. And then you have a switch, and then you have a boost converter to get 5 volt for the whole thing. This will probably be more efficient. Maybe.
Yeah, maybe.
We would need to try this, but this would be a alternative here. But I love the simple design here.
Yeah, the way it's done.
Yeah.
Okay, so if we go back over to the bench with my magic button, there we go, and we connect our load to here, and then we measure the current again. Shall we measure the current?
Oh yeah, on the input side.
On the input side, and then let's see how long we think this would run for once it's on. Okay, so I'll have to. It's probably
now you have to solder this. Yeah.
Yeah, I'm going to solder at least one of them.
Yeah.
So we solder that one on there.
Okay.
I will connect the load.
There won't be anything happen because I'll.
And then you connect the battery.
You need to get the thing running first. Wait. Go for it.
So can we see the meter? That was the whole. This was the whole point of this.
Too many hands.
Too many hands here. Okay, so.
All right.
You connected the battery.
I'm connecting the battery.
And I'm connecting the load.
Let's see if everything works.
Okay, so more hands are better than less, yeah. So,
okay, you guys can see the display down there. So, all right.
This is what friends are for. Yeah. So first of all, let's just test if it's working, and then we'll try and measure the current it's drawing.
Please do.
So I'll connect the thing. Oh, look, and the
output came on.
Output came on the
connection,
thing.
I think. Try again.
Yeah, because this is not lit up. Let's just go again.
Yeah. There you go.
Yeah, so we're on. Okay.
This is fine.
This is fine.
All right. Now we want to see the current from the battery to the whole shebang, right?
We certainly do.
Okay. Nice. All right.
So it's actually drawing 100 milliamps. It's a bit higher than my power supply is actually saying.
This is coming from the cell right now, so you need to include the up converting.
Up converting. So it's actually
we're coming from 3-point-something volts, and we're going up to 5 volts now on the output. So this must come from somewhere.
Yeah. Lower voltage needs more current for the same wattage, the same power. Okay, so 110 milliamps it runs. How long would this thing run on our battery?
Oh, let's see. There's your magic
thing again. So we know that it actually draws 110 when it's running. So it's saying
1 day.
1 day, 3 hours and 6 minutes. Okay.
Are you fine with that?
Well, is that what he's actually saying? Yeah, 1 day and 3 hours. So it'll run for a decent amount of time. In actual fact, yeah, I'm fine with that.
You normally use this for some hours.
Yeah, exactly. But a day, absolutely fine with me.
A day would mean you forgot to switch it off.
Correct.
Some of you guys mentioned that the switch doesn't need to be included, so we can simplify the design even further.
Yes, as Det mentioned, one of the subscribers said we don't actually need this switch. We can put a wire link in here. This is effectively setting it, and I don't totally understand this myself, but if it's acting as a transmitter or a receiver frequency for a radio receiver, it adds or subtracts 455 kilohertz IF frequency. Not something I need, so we can just take that switch out and put a link in there.
Yeah, it simplifies the design from the front panel.
Exactly. So we know it works. Now I think we need to look at the front panel.
We do. This was actually the thing that needed to be done. We needed to figure out if this works, because this power bank chip needs something 50 milliamps or something to keep working. Because otherwise, power banks, they switch off after 30 seconds.
If there's not enough load.
Yeah, and this was something we needed to figure out first, because this would kill the whole show if you can use it only for, say, 30 seconds.
Yeah, probably not a good idea.
Not ideal, right?
No. Okay.
Some of you guys mentioned looking into the software, doing a rabbit hole there. Not me. I don't have any use for these kind of things, so I won't do the deep dive into the software there. If you guys are interested to optimize or to switch this to something,
the firmware,
maybe you want to talk to the man here.
Yeah, and we can get your code to us and we'll load it in it and see how it works. I think the main thing people were saying was when we actually power this up, this band switch is switching to the popular amateur frequency bands, whereas somebody says, well, instead of doing that, you should go like sort of 100 kilohertz, 200, 500, 1 meg, 2, 5, and so on, and then you can just adjust it from here. I get what you're saying. I think the answer to that is all depends on the user, what they want to use this for.
Yeah.
To me, I mainly use it for testing things like oscilloscopes to see when I'm reviewing them, so it doesn't matter a lot to me.
Yeah.
So let's do the front panel first. This is not drawn to scale. You'll see it's actually a bit larger than that. Slightly larger that way. But on the front, really, we just need these 5 items. So we have an on-off switch. We have a frequency display. I think we'll just put frequency. We don't need the word display. This is the band switch. This is adjust. And this is your out, which is the BNC. Now, on the unit at the moment, we have a power LED, which at the moment isn't working because of the way we've modified it. But do we really need a power LED on the front of here? Because this display lights up when it's on. Yeah.
You will notice when it's on, yeah.
Exactly. So by omitting the power LED, in actual fact, it will draw less current. Actually, I'll say if we put the power LED on, it would draw more, because when we did the test of the current draw, the power LED wasn't connected.
Yeah.
So to me, it just clutters the front display even more, the panel, and we don't need it. And we obviously will know when it's on. So, as I say, it's not to scale. The other 4 things we need is the mounting holes to mount it onto the case. See if we can get the corners rounded like this. And that's basically it. So it's a very simple thing to do. So what we think, we have to measure this first. So we do the side as a PCB, and then we can kind of work out with a little caliper the size of the holes we make. This is going to be the most difficult one, I would think.
From here on, this is all just doing.
We do this yet. Exactly. And this little header, we actually unsolder this, so we have a flush side of this where the display is. And then we still have the pads on the other side where we can solder from.
And we do simply traces on the back side, so
exactly,
we can do some flat things on there and then connect VCC, ground, SCL, SDA, so I2C is connected.
So there will be a few traces on here, 3 traces plus the ground panel. Okay, well, let's get on with it then. So we need the calipers.
Let's go. In this layout software here, there's a thing that I can set a board outline, and I can set the board outline with rounded rectangular, so I'll have rounded corners.
Okay, nice.
What do you say now? And it's all in millimeters, so we need a width of
150
by a height of 40. And now the big question is, how big will be the radius? This way, I think. So I'll try to figure out where the rounded bits start, and this would be 2 mil.
2 mil.
Yeah,
okay.
2 millimeters. So let's see how this looks. Apply.
Yeah.
Well, it just looks pretty much like 1.5.
It certainly does. It certainly does.
Yeah, nice. Okay. I can live with that.
Okay, so that's the size of our PCB.
Yeah. What I did wrong here is I should have set it to the 0 point. So I'll erase this. Do this again. Tools. Set board outline. Rounded rectangular. So this should be 0.
Okay.
What we have now is a nice thing that fits right into the 0 point, so we can measure from the 0 point. What I did here, I changed the grid and the snap size to 5 millimeters. So you normally wouldn't do this for a PCB layout, but this time it's okay. So now we have our outlines. These are our drilling holes.
Yeah.
I'll copy this right now, and then I'll move this thing to touch the things here. And it does. So last thing to set. Yeah, this looks fine.
Okay.
So now we have the mounting holes here.
Okay. The width of the display, 25.
25, yeah.
And the height of the display is 16.5.
Okay.
Okay.
I got the display here. Width was 25.
Yep.
And the height?
16.5.
16.5. Alright, there we go. This needs to go somewhere here. So what I'm doing now, I have a rectangular here. This is a rect property, but I can't do the board cutout with that. For the board cutout, I need the solid region.
Okay.
What I'm going to do now, I want to use the outline of the rectangular here as a guide.
Okay.
So I'll go in for this, and I have to move this somewhere where it, now I've locked it. No, where it actually fits into the grid, because otherwise it won't snap to the grid.
Okay, fine.
Yeah. Now I'm going to lock this again. Going for solid region. I'm going for ding. You maybe can't see this. This is moving over here.
And
go. Oh, come on. It will be a bit bigger. Go there and go over there. So now we have. If I need to unlock this. No. Move this out of the way. Now we have this thing over here.
Okay.
And I can go for crap. I used the wrong one. Of course I did.
Control Z it a few times, then go again.
What did I use here? Solid region. Oh, there's it. There it is. Sorry. Yeah, solid region was right. If I go here, solid region, and I type is now solid. And I could go for a board cutout.
Okay.
And what we have now, if we go for the 3D view, there's a hole in the board.
Okay, for the display.
Yeah.
Is it the size we want it to be?
Pretty much.
Okay.
Good enough for Australia, you know.
Okay, fine. So we now have a board cut out for that.
Yeah. And we could move this. So
Great.
You can move this any way you want. I don't need this thing anymore. This can go.
Okay.
So now we need the buttons.
Well, that's fine there. And then band just slightly over on the center line. I'd put band nearer to the switch than nearer to the BNC.
All right. Let's go.
I think that looks nice. And then the switch
isn't centered.
Yeah, that's
now
centered.
It's centered. Yeah.
And then the switch on the left, just slightly to the left. Yeah.
Yeah, I would go slightly to the left. Yeah, like that. You're fine.
I think that's fairly fine. Can we just switch a bit more left?
Right? A bit more. Right?
Bit more left. I'm just looking how the proportions of it look.
Yeah.
That actually looks nice.
Yeah. Display looks good. It could be a bit more. Oh, what did it snap to? Snap to something. Well.
Yeah. Put it slightly higher. I think. Yeah, that's fine. I think that's fairly central. And then we can just look at the sort of distance from that to each of the switches. It looks about right.
I'll show you on the 3D view. This will help more.
Okay. Yeah.
Wow.
Wow, so there's
That
our
came out good.
front panel. So what we need to do now is to put some traces on the back because...
Let's do the important part first. Let's do some writing on this.
Oh, of course. So the switch, I think we can just say on.
Yeah, this will be on the top silk layer. So let's go here. And There's a text tool, of course. And we need on. I do caps here, right?
Yeah.
You want to have this on top or you want to have this below?
Whichever. Up for on or down for on?
Let's see.
Maybe down.
Maybe down.
But there again, where we're going to put the other options, band and adjuster, we're going to go below and then the display one above. Let's try it.
Ooh, man, we should be professional interface plates
We
designer.
should be, shouldn't we? So that's our front panel.
We were a bit off camera here because I need to figure it out. We needed to figure out some things before I tell you people, because this is the first time I'm doing this. So what we need to do now is to get the electrical parts here going. So we have the front panel done, but we need to do the little thing with the display here. So this has 4 connections. This is ground, VCC, SCL, SDA. And what I needed to have some pads on the back side of the PCB. I can show you in the 3D view here.
Okay.
So on the back side, if I move to the back side, you see
there
are our pads. So I need to expose the copper there. So this will be our pads. So what we did here is, I measured the distance between the middle of the mounting holes, or somewhere in the middle of the mounting hole, and the actual outline of the little display. So this is the outline of the display, and this is somewhere where the first pin is. The same on the other side because it's symmetrical.
Yeah.
And what I did then, I did these 4 traces. So this is ground, VCC, SCL, SDA. So now we know they are equally distanced spaced.
Okay.
So this should fit the thing. I'm doing a bit of guesswork here because we did all the measurements in millimeters, and these distances are of course inches.
0.1 of an inch, yeah.
Yeah. So this, I think this is probably the easiest way to do this, because since they're equally spaced, this must be somewhere
it must
around
be about
there.
right.
Yeah, and you always have some leeway here. What I need to do now is select them all. 1, 2, 3, and 4.
Okay.
And there's this button over here, expose copper. So now they turned white.
Okay.
And if I go for the 3D view and go on the back side.
Yeah, bare copper pads.
So we have our bare copper pads, and these will be beyond. This will be the connections to the little display, so we don't have cables flying around for everything here. What I need to do now is get some wires over here. So we have somewhere over here another part that we can connect wires to go to the main board.
And also to the clock module.
And the clock module will have another set of parts there.
And there you go, guys. You can see this is the front panel. Det just wanted to put this on there, so he was doing the design work. I let him do it. So you can see on the back of the board we have some connections, a few tracks. Most of it, this is just ground plane, so effectively we have a metal case and we have a metal plane on the front panel as well. We have a few connections here, so VCC, SCL, SDA. These connections will be coming from the actual board that the project is built on, the signal generator board. These ones go to the display. So the display inserts into here. I'll just show you the display in a minute. Instead of having the pins we normally have, we're just going to solder the pads on the display directly to the pads here. And then this one is for connecting to the actual clock generator board. So this is where the BNC fits in. The clock generator PCB is sticking backwards out of here. So over here is going to be effectively the pins, and we just run some wires. So that's it. That's all the connections made. This is the little clock generator then. So we're going to unsolder these 2 connectors. Just this one. In fact, we unsolder this one as well, and we replace it with a BNC because this is pretty much a universal type of connector. This then inserts into the front panel, so this will go through the front panel like so. We've made sure there's enough clearance for this PCB before the next control, which is the rotary encoder, so it will fit quite nicely. And then you see these connections on the back, so we can just run wires from these VN, SCL, SDA down to the front panel PCB we've just designed.
We did.
Okay, so that's basically how that goes together. The display fits into the board. So with the display itself, I will unsolder this little pin header here. So under here, effectively, we have pads. We'll see the solder pads. And I need to get a connection from the solder pad to the actual pads we put on the PCB. Don't worry about it, guys. I'll figure a way of soldering that. He says. Okay, I'll worry about it later. You guys don't worry about it. But I'm sure I can do this, even if I have to tag some very fine bits of wire here, stick it in, and then just solder them from here.
Yeah, that would be probably my choice too.
Where there's a will, there's a way. We'll do it. Regards the rear panel, this will just be effectively plain. It will have the connection on for the USB-C. This is the charging port, and a connection for this one, USB-A. This is if we use it as a power bank. So we need to get these to stick through the back of the panel, and we need to mount them some way. So the best idea I can come up with.
Hot snot. No, not hot snot.
No,
right?
it's not hot snot. It's better than hot snot. So this is where the panel will go on the back, okay? If we mount this board as far back as we can, bear in mind that this display will no longer be here. It's on the front panel. And the module that was here is on the front panel. So you'll see that we have here like a mounting hole, and I'm pretty sure we can actually mount our USB-C through that hole, considering this will no longer be sitting here. So it's all flat under here, yeah? So we can mount that one there. And then if we put the board right to the back, we can position it so that this is sticking through a little slot in the panel, which we made from PCB material again. And the same with the other USB connector. I'll have a lot of space here. Now, this one we need to fit something like this angle. I think probably we might even be able to just drill another hole away from these tracks. Obviously, you see we have like a mounting hole here, and we can probably, yeah, there's a lot of space here, so I'm fairly sure we can just drill through there. There's no other tracks, it's single-sided. And again, just position it so that when this board is mounted through into some pillars into the case, these just stick out to the back. So the board is inside, obviously. Yeah, and these stick through. So that's how I think we'll do that. The bottom of the case has a little feet on. If I actually use the bottom, this is the feet. So we can get some little pins through here into some mounting posts for this. No problem. So guys, you can see I've taken off the components which are going to be mounted on the front panel. I have some space now. Just temporarily, I've actually glued these on, the connectors. You'll see they're not level, but you'll notice here this is one of the mounting points for the PCB. So we're going to have a bolt coming through here. So in fact we can put a spacer or one nut and then this board and another nut. We can set that up so these two will effectively be level. Let's be mounted a little bit higher up. This one, again, I can actually get a bolt through one of these. I think this one. I may end up having to reroute this track, I'm not sure. Yeah, I think I can get through this way actually. So I'll put one mounting pillar again in there.
It doesn't really matter because we can grab everything from the other connector to the front panel.
Let's have a. Oh, this is true actually, as Jets just said. These tracks are not used. We can take them all from here. Okay, so we have no problem mounting. We can actually cut these tracks. We don't need any of these anymore because, as you can see, the SCL and SDA, as well as going to the display, go here. So this is all actually obsolete, these tracks now. Okay, that makes it easier. So we can actually get a couple mounting bolts through these. We don't need anything holding them like glue. We can put some spacers so they're the same height as each other. So that's how we're going to do that. Nice one, Dad. So from that, we can get the measurements we needed. And once we have the measurements, it was easy to design the back panel. So Dad, show us what you've designed.
Let's go. This looks way more cleaned up than it was while I was designing the thing. There's not much going on the back plane here. We have a V in for USB-C. This is this cut out here, and a V out with a USB-A. Is this, I think?
Yeah, USB-A. So that acts like a power bank.
Yeah, the emergency power bank here from the thing,
which is always handy.
Yeah.
So what are those little things you got over to the left there? Those things.
These are somewhat experimental because. You see the blue part here. The blue part is one big ground plane. And what I wanted to have, the little controller module has 4 LEDs.
Oh, the charger module.
Yeah, tell you how the power levels in the cell. So,
okay.
What I did here, I left 4 cutouts in the ground plane. Maybe you're going to see this in 3D view. You want to have a board probably in black, I think.
Yes, black is nice. Yeah, I like it.
Oh yeah, there you can see this.
I see.
Yeah. So this would shine. The LEDs would shine through the PCB itself, and maybe look cool.
It might look good.
Yeah, this is a bit experimental here. Let's see how this looks when I get this back.
Good idea. So we'll just show you what we're talking about with the LEDs on the little charger board.
Yeah. Okay.
So this is the little board that was discussing. Because nothing's been plugged into here, there's no kind of pressure on, so a bit of hot snot or something or glue, just stick it to the rear panel, and then these LEDs will shine through those areas he's made with no ground plane. And then hopefully we have some sort of charge indicator as well.
Yeah.
So guys, you can see we've designed a front panel and a back panel for this project. It's a nice metal enclosure. This is ideal for an RF signal generator. We have back planes on the front and back panel, ground planes I should say, so it's all shielded nicely. We know where this is going to fit, and basically all we need to do is put this together so that these line up with the holes. I don't think there's anything else much more to do today, Dad. I think that's
no, actually not
everything.
And you know, people saying, okay, you can use, of course, you can use a 3D printer for that, but you know, I'm more used to doing EDA work, so yeah, this is more easy for me. This is more home turf.
I think this will look a lot more professional than a 3D printed enclosure. So
that too, yeah.
Let's look when they turn up. Let's have a look how it looks.
And one thing, this isn't plastics. This is fiberglass. So this is mechanically way more stable.
Yeah, and we have the copper plating on, so it's also shielded. Of course, guys, you might have some better ideas. Owen,
only is.
Yeah. So any ideas, anything you want to add to that before we upload this to PCBWay and get them made, let us know. We'll always revisit it if somebody's got some good ideas, or something you think we just didn't do right, let us know.
Could happen.
Yeah, it could. So you know where to get, guys, in the comments below. Yeah, down there. That's your finger. So let us all know. Look forward to seeing you all soon again on Learn Electronics Repair. Wait for it. Ciao guys.
We always get this wrong.
but that'll work. Rather wait for it, and it's